Io non voglio via la trascrizione.
Ma chi se ne frega?
Ok, via.
Good afternoon and welcome and thank you for all for attending our fourth webinar organized in support to the MOOC Essential Radiochemistry for Society. Just a few words to introduce our special guest, Professor Teodora Retegan Vollmer. And Dr. Teodora holds two habilitations for teaching and training in higher education, the first one in hydrometallurgy and the second in nuclear chemistry. She has been the first female associate professor in nuclear chemistry in Sweden, and now she is full professor at Chalmers University of Technology. Professor Teodora is very active in research on nuclear chemistry with competencies in solvent extraction of metals from spent nuclear fuels and also of platinum group metals from electronic waste. She is and has been involved in several international funding projects concerning partitioning and transmutation and the generation for nuclear reactors, and also in the role of domain and VP leader. And Professor Teodora Retegan is also a representative at Chalmers in NN. So enjoy this webinar, and Theo, please, the floor is yours.
We are going to have an outlook on the evolution of nuclear power in the world. We are going to talk a little bit about nuclear safety, about fuel metrics and cladding, what type of fuels, what type of claddings we can talk about or we have had in the past and what we are going to have in the future. We are going to talk about a very important part of a reactor, and that is the coolant. Then we are going to discuss about the performance of the fuel and fuel assembly, along with the cladding, which is surrounding the fuel, because that is also one of the very important aspects of safety. And then we are going to go through the fuel, coolant, and cladding interactions. What happens when these three main barriers are basically together, what is happening with them, and what will happen in the future. And then, of course, we will have the conclusion of our overview. So please go to next. When it comes to the evolution of nuclear power, we know very well that nuclear power has started not so long time ago, if we think about many other industries, but it has been going quite strong since then. And we are today very close to deploy both generation 3 and generation 4 reactors in the world. But here we can start maybe with the so-called generation 1, where we have around 1950s the first commercial reactors coming into the grid and started to connect to deliver electricity. Then we have the generation 2, which is basically the current fleet reactor, and also partly generation 3 we can talk about, which are also currently connecting to the grid right now. And then we can talk about generation 3 plus or generation 4 reactors, which we call now for also fast reactors. And the reason is, of course, that the neutron spectrum of the future reactors is considered to be a bit different of the current fleet, which most of it is thermal spectrum. So this being said, you can see different type of nuclear power reactors which have been developed in the world and deployed until current days. And some of them, when it comes to the generation 3, 3 plus, and generation 4, you see some prototypes, or at least on the paper prototypes, types of reactors which we are trying to study, and some of them have already been discarded for the future application of the nuclear power in the world. Then, of course, the most interesting part is that the next generation reactors, and also partly the current generation reactors, they reuse part of the fuel which has not been depleted or used in the first stage. That means that we can have much better fuel economy, and we can take care also of the waste which is remaining. That means that by recycling the nuclear fuel, we will diminish the time necessary for the final repository. And we are also diminishing the volume necessary for the final repository because, of course, the volumes will decrease. Even more, if we manage to burn some of the fission products which are having a lot of heat which is released, then also the volume will be diminished, of course, because this is also an important parameter. When you have the fuel down into the ground, it doesn't have to be very hot and not for a very long time. With this being said, let's dive a little bit further. Please, next slide. So what are the common designs which today we can say that we have them in the world? Here you have a table, and this table you can see that it has been taken from a review paper. But it's not only what type of reactors we have, but what type of material, the fuel, which one is it, what is the moderator, what is the coolant. And of course, it's very interesting to know the cladding and some operating parameters. So you can see that we can talk very much about gas-cooled reactors, pressure water reactors, boiling water reactors, pressurized heavy water reactor, advanced gas-cooled reactors, and high power channel type reactor. And you can see that the fuel is mostly uranium oxide, but we do have also mixed oxide fuel. That means it's uranium oxide and plutonium oxide mix, so-called MOX. And then when we talk about the moderator material, you can see that it can vary already today. We can have graphite, but also we have water, so-called light water, and we have also the heavy water when it comes to the pressurized heavy water reactors. And when it comes to the primary coolant material, you can see that that also can be different, but in some cases we have the moderator and the primary coolant material the same material, the same thing. So I'm speaking mostly about the water-cooled reactors, which is basically one of the most used type of reactors in the world right now. Now, when we're talking about the cladding material, what type of cladding material we have magnesium alloys, but we have zirconium alloys, so-called zirc alloys, or we can have austenitic stainless steel, which can be put in advanced cool reactors. That means that higher temperature reactors are using this type of cladding material. Why it's important to know that? Well, if you just think about not so many years back, Fukushima had a very spectacular explosion of gas that has been catalyzed by the material existing in the cladding material. So when you talk about zirconium, which is in the cladding material, there was a great catalyst to form a lot of hydrogen gas, which managed to increase the pressure, and then everyone has seen this explosion, which in reality at that time, in the beginning of the reaction, has been a gas explosion. Then it developed to something else because of different other failures which have happened. But so this is a very important real life case why materials which are used in the reactor are very important. And the design of the reactor is very good to know, because then thinking about what type of chemistry can happen, some materials, when they can react with each other and they have proper environment to react with each other, they can play a very important role to the safety. Please, we go to the next slide. Then when we are talking about the design for the generation 4 systems and also the 3+ system, basically, we are talking about different types of nuclear reactors. So we have the gas-cooled fast reactors, lead-cooled fast reactor, molten salt fast reactor, molten salt reactor, advanced high-temperature reactors. You can see also that the spectrum is sometimes fast spectrum, other time is thermal spectrum. So you have it in the next column there. Then we talk about sodium-cooled fast reactors. supercritical water-cooled reactors, and very high temperature gas reactors. And then you see that the neutron spectrum differs very much. And this is basically because of the type of the fuel you have in the reactor. So if you are looking a little bit at that, you see that the fuel will change. It's not only uranium oxide or MOX fuel, but there are other types of fuel. And this is because this type of fuel is already recycled and is basically now probably at the 4th or 5th cycle in a reactor after their first use. The coolants also are changing. The reason is that having a fast reactor spectrum, then you have to look what do you use in order not to thermalize the neutron, not to stop their speed. And then, of course, you have to think about the safety. So then we have different types of coolants. We will talk a bit about this later. Temperatures, they can vary very much, but you can see that compared to today's reactors, temperature is slightly higher in some respect and much higher in other respects. That means that we have to have the structural material changing slightly, and they have to be able to withstand a lot of chemical reactions, which otherwise they wouldn't have had to be when you think about the light water reactors we have today. Then, of course, it's very important to think about the size, how big you want to have them, because today we have rather big nuclear reactors. There is a tendency today that we are going towards, or the trend is that we are going towards the small modular reactors, mostly out of simplicity of use, and also some other reasons, which can be maybe safety of the integrity of the reactor site, or simply that the areas where they can be installed are widening, in the sense that maybe in the Arctic, where there is a need of a lot of electricity, for instance, maybe a normal power plant like we have today with these big reactors is not so easy to have, but a smaller modular reactor, it would be much easier to place in those locations. And this is one of the reasons. Of course, there are much more, and I don't have today this in mind to talk about. But anyway, keep in mind that all these reactors we have here, at least half of them are foreseen to be small modular reactors. So not all of them are fitting for that, but some of them are. And here I'm talking about mostly the salt cooled reactors or metallic cooled reactors. Next, please. So how about nuclear safety? What are the primers of the nuclear safety? Well, we talk about hazards. What hazards do we have? What are the most important? Fission products are highly radioactive, and some of them are also toxic by themselves. They don't have to be necessarily radioactive. What is the aggravating factor when we talk about nuclear safety? Well, a nuclear fuel can never completely be shut down. So we have the decaying head, we still have reactions which are ongoing, chemical reactions, but also we have, due to the heat, you can have all kinds of different metallic phases which are still modifying. And what are the objectives when we talk about nuclear safety? Of course, objective is to prevent the release of radioactivity into the environment, and of course, interaction with human beings. So for this, there are two main safety pillars we can talk about. There are much more, of course, but these are the main safety pillars. One is called defense in depth. That means there are multiple independent physical barriers. And which are these physical barriers? Well, first of all is the fuel, and the fuel pin, and the vessel of the reactor, and then we have the containment of the reactor. So all the components of a nuclear reactor are built with safety in mind. So they have to withstand by themselves stress. And safety systems, which are adjacent to all these, are of course put in place in order to prevent overheating of the core when the normal coolant is lost. Now, talking back to about Fukushima, you remember that one big disruption has been that the station had to endure a big tsunami wave, which washed away aggregates and everything which could actually help up with the electricity on the site. If you don't have electricity on the site, basically your pumps are not working properly. That means that the coolant cannot function properly. And then even if you have other systems which can prevent a very big accident, also maybe some of the systems are not perfectly functional. So basically, there are a lot of redundancies which not necessarily they need electricity, but electricity makes that the water or whatever coolant you have can be pumped, and then you have other problems a little bit later in the development of the accident. So then you have all these redundancy systems which are preventing overheating as much as possible. And it's not only water, because if you think about this, nuclear fuel by itself, the pellet has to endure a very high temperature, but we also know quite well how long time it goes until that starts to melt. So they knew already then, they had calculation previously made at the site where they knew that they have some hours until they can go towards a local meltdown in the reactor. So you can see that there are a lot of safety put in place. There are only a few words here, but it's a much, much bigger part. And every reactor has this type of calculation. So basically we know all the steps on the way, what system can fail and in what way. So this is a lesson learned from the past happenings and also from the tests which were made before the reactors were even built. Let's go to the next slide. Thank you very much. So the physical barriers, as I said, it's a very childish picture, but probably it's quite easy to understand. We have the first physical barrier is the fuel. And you can see here that the fuel pellets, they are stacked and encapsulated together, and you have the cladding material around them. So basically here is the second barrier, and all these are stacked together and put in the fuel assembly, which is the third barrier. And the fuel assembly is in the core, where here in the reactor you have this small red dot. It's put in the vessel, which is protecting everything. So this is another barrier. And then you have the reactor containment. Here you have some better picture where you can see in 3D almost how the interior of a containment and where the core is placed. The core is here, the red part. So you can see how many systems around you have in order to prevent any escape of any radionuclide which can possibly escape by mistake from the core of the reactor. And then, of course, all around, there are other systems which can, if the containment is still is not damaged, then all the other systems here, they are made with the thought that they should be independent and that they should not come in contact with anything which could be in here. So that means that we have these heat exchangers here. Basically, the systems which are in the reactor, they shouldn't come out in contact with anything which goes into steam or anything which goes to the turbine. So there are a lot of redundancy systems, and even these systems, they still do have additional redundancy. So it is one of the industries which takes safety very seriously, and it's continuous learning. And the overall aim for all this is, of course, that nothing should end up here in the city or anywhere where humans are present, or animals, or nature in general, because of course this can create a lot of problems. Let's go please to the next slide. If you think a little bit about how how things are handled today at the nuclear power plants and how safety is all the way until the fuel can be taken down to the final repository. Here I have the example of Sweden. So you can see that you have the fuel, you have the cladding and the fuel, you have the fuel, you have the reactors here, you have several power plants where you can have different type of reactors. For instance, in Oskarshamn, you have boiling water reactors, while at Ringhals, you have some of them are pressure water reactors. And here we have another boiling water reactor. So the type of reactor can vary. What is happening with the fuel? Basically, after you use the fuel in the one cycle or several cycles, you take out the fuel, you have the fuel in some pools which are very close here on the site. You have the pools where you can keep this fuel up to 3 years. And then you have to transport the fuel to an interim space. In Sweden, the interim space is called club, and it looks like this. There are some swimming pools quite deep where you basically can store in these capsules the used nuclear fuel. And here it will stay up to 40 years until it's cooling down enough that you can actually put them in the capsule, unless you want to recycle them, of course. Put them in a capsule and then you can put them down into the ground. So right now in Sweden, actually, this is the fuel cycle. It's not a closed fuel cycle in that sense that you can recycle, but it's a closed fuel cycle right now in the sense that you put it down into the ground. And this is the projected final repository in Sweden. However, if you recycle this fuel, which is in the interim repository, you still have left, of course, nuclear waste. And then it goes the same way. It has to go into the safe repositories. However, the time probably will be much shorter, depending on how many times you are recycling, and also the volume will be much less. But you have to think that all the way, even when the fuel goes out from the reactor, safety still applies, and it has to. So in this respect, you have here a boat, which is a very special type of boat built for transportation of such a fuel. So let's go to the next slide, please. Next slide. Thank you very much. So now we are going to talk a little bit more about the fuel matrix and the cladding, because this is very important part of the safety. As I said, this safety goes from the beginning to the end, and it's depending on the materials which are present in the fuel matrix and also the cladding. Why do I say matrix? Well, because you have different type of compositions and chemistries in a fuel, and you will see that it can be quite complicated chemistry, and also cladding can be quite different. So let's go and see the safety. When we talk about nuclear fuels, there are quite many types of nuclear fuels we can talk about, and they can be either commercially available already, or they are under evaluation, some of them, or they're under research. And the most used right now in the world are oxides, and you can see that you have the uranium oxide or MOX fuel. Then we have the metallic fuels, which were used in the Magnus reactors a while ago. Carbides, which are still under evaluation and research right now. We have nitrides, where also, actually in my group, we are making quite a bit of research on the nitrides right now. So it's one of the fuels which is already under evaluation. So it's one step further from the research area. Then we have the metal alloys. We have the index matrix fuels, and these inert matrix fuels are basically in the ceramic forms. And then we have a plethora of other type of nuclear fuels which are under research, and some of them are quite advanced. So if you look at this triso, for example, which is basically tristructural isotopic fuel, the the beautiful golf ball, it looks a little bit like that. This is actually quite advanced. It's one of the most promising nuclear fuels because it's extremely good when it comes to safety. And why is that good? If you look at the layers of the fuel which are here, you can see that basically from the fuel kernel, which is the one which is basically used for real in the reactor in order to have energy, you have a layer of materials which are very good to withstand very high temperature and also pressures, which in this case is not that high. So you reduce significantly the pressure inside the fuel because of the type of coating you have around the fuel in this case. Then you can see also here, this is a real picture. So you see how the kernel looks like in reality. And they are currently tested in US and some other countries, and the results are quite good. This is going to be placed in the type of reactor which will have fast spectrum, but it can actually be tested in different spectrums. So that's also the beauty of this type of fuel, that it's withstanding quite many different environments. When we talk about the current fuels, this is, you can see some picture of a uranium oxide pellet. This is probably the most common, and many of you maybe have seen it already. And then we have also the CANDU fuel, which is natural uranium oxide pellets. And you see the geometry of the bundle, it's slightly different, it's round. So that is because of how the fuel bundle looks like. We are going to look also at the fuel bundles. You will see that there are different geometries. So next slide, please. Before that, we are going to look a little bit at the cladding materials. And as I told you before, cladding materials are very important for safety. And this is why. First of all, it's because of the materials they are made. They can serve as protecting the fuel, but they can also be in proper environment, play the role of a catalyst. You know very well that catalysts can speed up reactions, and then you can have chemical reactions which are not necessarily desired in a nuclear reactor, which can lead to severe accidents in the end. So we have the well-known zircaloy, and you have it. It's this quite shiny, beautiful color. Then we have stainless steels, depending on what type of reactor you are using. But here we can look at the Cantar type of FECRAL. It's called the material. And then we have all kinds of aluminum alloys for research and test reactors. We have all kinds of refractory alloys, which are withstanding very high temperatures. So these are mostly used for gas type of reactors, which have much higher temperatures for functioning than other reactors. And then we have also some research for the ceramic matrix composites. And I can say that there are quite many, but none of them actually is right now desired for operation. But this has been also a very good proposal, because you can think about when you have different layers of composites, they might withstand pressure and all kind of deformation, maybe better than a metal. Sorry, here you have a picture of titanium 15 austenitic stainless steel, which is projected to be used on some research reactors right now, which are cooled with lead or lead bismuth. So in this case, you can see that there are a lot of tests which are conducted to check how easy this type of material can be destroyed. So these specimens, you see that they are used in order to stretch the material and see how ductile and how long you can stretch it until it will give up. So this is the reason I put the picture here, to see that there are all kinds of experiments made for the safety of the cladding materials. And that means that the material chemistry is one of the very important fields which, besides nuclear chemistry, they have to be taken into consideration. And of course, they will have all kinds of chemistries included. Let's go to the next slide. When we talk about the coolants, here we have also a very important part, because of course a coolant can play a very significant role as the barrier, which is almost the ultimate barrier before everything goes out from the containment of a nuclear reactor. So they have to both cool, and most of them, they also have the role of kind of retaining some of the fission products which are produced in the nuclear fuel. So historically, we have very interesting coolants, and you can see that there have been a lot of liquid metals which have been used, and we have had mercury, we have had sodium, we have had potassium, lithium, and so forth. And then today we are looking very much at lead and lead bismuth eutectic as being the most inert of the group. If you look at it and you think about lithium, what can happen with lithium, and you have seen a lithium fire, then you understand how safety can be there or not. The same is with sodium. But sodium is actually a well-proven technology, which we know that it has been working quite well. But today, it's a lot of emphasis put on the lead and lead bismuth type of coolants. Of course, we have the molten salts, which is also a very important type of coolant, and today it's also one of the interesting coolants which we have. Then we have the water, which historically has been first, it has been heavy water and light water. Heavy water actually has been more research in the beginning for reasons well known. We know that heavy water, it's a good moderator for certain fission reactors. And then we have gases, and here we talk about helium. These are mostly for the very high heat reactors. And then we actually had organic compounds, the PCB, polychlorinated biphenyl, which was actually used in a very small reactor, Picoya generation station in Ohio, in US. So the present fleet, we have water and we have a liquid sodium metal. And the future, as we talked before, we have gas-cooled reactors, water-cooled reactors, where we talk about supercritical water. That means that the pressure and the temperature are a bit different than the normal light water reactors or even pressure water reactors. Then we have the molten salt, and then we have the liquid metals. So what are the properties to be fulfilled of these coolants for safety? They have to have efficient heat transfer, first of all, of course. Then it has to be fluid in a way that it can fit in all the places and spaces which are in the core, so that they don't have to leave bubbles anywhere, because then you will have a difference in temperature, and that difference in temperature can lead to accidents. Then it has to be thermal and material compatible with the structural materials. It has to be, of course, chemically stable at high temperature. And then if you look at it and you think about the organic compounds, that doesn't really fit the picture. Then, of course, they shouldn't be corrosive, and they should have a poor neutron absorber. Why that? Well, we don't want to stop the neutrons when they go through, so they want to start the fission. When you talk about non-corrosivity and you look at the future, you can see very well that corrosivity, if you look at sodium, lead, or lead bismuth, you realize very quickly that this will be a corrosive environment. That means that you have to have other factors which have to be added to the chemistry of this type of coolants. In this respect, you will have a cover gas which doesn't have to be air, or it has to be very poor in oxygen. That means that you will have probably argon or some neutral gas, which can be the cover gas. So we go further. And here you have the examples of some of the reactors I have been talking about. So you see that the first little experimental nuclear reactor here, the EBR2, which was cooled with sodium. It has been in the desert close to Idaho Falls in US. And this was the first time when more or less reactor has been connected to a grid, and they had 3 or 4 lamps which were light. So that was the beginning of the era when we started to have commercial reactors. Then you have some of the advanced gas reactors. Tormes Power Station in Scotland, which is pictured here. You have also this very interesting reactor, which was cooled with organic coolant in the Piqua generation station. And here we have the picture of the first fast reactor, which we call it now generation 4. It was not really a generation 4 reactor, but many of you have heard about it, Clementine. So the Clementine reactor has been cooled with mercury. I was working with the plutonium-39 fuel, and it was in operation between 1945 and 1954. So it has been a very little reactor, and you can see that the control room was not so impressive. So it could be actually operated by not so many people. But it has been one of the milestones reached when it comes to reactor safety and also reactor design. That's why I said that there are a lot of lessons which are learning from the past, because a lot of the research reactors we have had in the past, as you can see, today we call them generation 4, and they have a lot of improvements we learned since then. Next, please. Now, when we have been talking about the fuel, the cladding, and the coolant, we want to see a little bit the designs of the fuel assembly and the cladding. And you can see that depending on the type of the reactor we are talking about, you can have different geometries of the assemblies which are put into the reactor. So these geometries, they have some functions. They have to provide support and protection for the fuel pin bundle and other components. They have to provide the control path from the primary coolant so it can flow through all these channels. You can see very well that you have channels which are in between here, and also provide compact and structure unit that can be easily moved in and out from the core. And why that is important? Of course, it's important for refueling of a nuclear reactor. And of course, these have to interact with neighboring subassemblies in a way that ensures safe and predictable reactor geometry, because according to that, the calculations for the core well functioning can be done. So if you know the geometry, the exact geometry of the core, then you can also determine ahead possible happenings and possible behaviors you can prevent. There are, however, of course, issues which we are continuously implementing and try to improve. We have swelling, which can happen in the material. We have creep, which can happen. I will explain a little bit later what all the term means. Fatigue and toughness. And then one of the paramount importance is actually the reduced limits of the weldment. So when you have to weld something, that is basically defect you introduce in material knowingly. So you know that, okay, here the material doesn't have the same structure anymore because it's a weld, and you know that this exists, and you know how many you have and where they are. So these are the design issues which we know. Next, please. If you think about the fuel rod, how it looks like, this is a commercial fuel rod example. You probably have seen already that you have the fuel pellets together here. You have the, I'm sorry, I have somebody which wants to come in here. That's it. You have the upper reflector and the lower reflector. You have the springs which ensure that basically when the fuel is swelling can move inside the tube. And also when we have gases, you have the gas plenum here. The gases can be released in this direction. So this is basically already a lot of the safety features which are inside the fuel rod by design. So you already prevent some things which will happen due to irradiation when you start producing, this is, by the way, fuel rod which is made for oxide fuels. And in their case, we can talk about significant release of gases, and also we have the volatile products which are released, which will end up in the gas form. So that means this plenum will fill gradually with different compounds and gases resulting from the irradiation. So knowing this, how the fuel rod looks like, then you already have a very good case where you can prevent and know the behavior of future behavior. So this is the safety of the fuel pin, we call it. And of course, this together with the rest of the reactor is going to be, in a way, easy to prevent and calculate certain events, unless it's a sudden thing, which you cannot prevent at all, like it has been a natural disaster. Next, please. When you think about the performance of the fuel assembly and cladding, we were talking a little bit about what they need to withstand, and the cladding has to survive, and it has to be very predictable. So wastage we were talking about is basically the corrosion by the coolant. The fuel cladding, chemical interaction. Also, I told you that you have a lot of interaction. It's material chemistry basically here. And then you have also the mechanical part, the mechanical dimension, where you have the mechanical interaction, the fretting. Fretting is basically when the coolant goes by the walls of the material, and then you have potential damages which can happen during that time. Then we have strain. What is the strain? Is the fission gas pressurization. As I showed you before, you can have gas release due to the fuel irradiation. Then you have the swelling associated creep of the constrained components. So, of course, if it's too much overpressure and you also have this heated surface of the fuel, then you have a material which is a bit more elastic and it's easier to modify. And then you will get a bit of swelling. Of course, if you have some defects which are coming from the design, or they're simply coming from the production most of the time, then the swelling can find such a spot, and then you can form a little bubble, basically. And then, of course, we have here as well the fuel cladding mechanical interaction, and that means that eventually when the swell is too much, the cladding and the fuel, they come in contact, so you don't have the gas around them anymore, but they will come in contact inside the tube. So in order to prevent accident and thinking about all the steps we have been talking before, it has to have microstructural stability during accident transient. So you have to know down to the microstructure what could have happened. So you know what type of material you have, and you know the potential defects which you can have, or the potential defects you induce, like the welding, and then you know the microstructural stability, at least at the higher scale. Next, please. So when something happens, what can happen? Well, a lot can happen, but when you take it down to the fuel during operation, you can have a sudden tightness loss of the cladding. So as I said, you have potential defects, or you can have stress-related damages. And this will lead first, well, here it says that will lead the coolant to enter the pin, but first you will have a very small pore, and that pore will probably make it easy for the coolant to try to enter the pin. And the result can be a possible fuel coolant interaction. So the coolant will come from the outside and interact with the fuel inside. Now, depending on the operation condition, the products of the reactions, when you have the small pore, they can increase in size, and basically they are growing like a crystal. It's not really exactly a real crystal, but this is just to emphasize how it can happen. And this can increase the size of the initial breach to a secondary crack. So you can really have a crack in the material. And then in the final stage of the evolution, the fissile material can leave the pin. And what is leaving first and how, it depends a little bit on the type of the damage. But of course, if it's a small damage, then you have this kind of steps. So you have the volatile species going first, of course. They are going to be followed by extremely small grains, which are resulting from the crack of the fuel during the because of the burnup. And this can also contain heavier actinides if the material comes from the center part of the fuel. And then basically you can have a release of the material into the coolant. Of course, this situation must be avoided at any price, but it is happening. Next, please. So if you look at the nuclear fuel, how it can look after a certain time in the reactor, you see that it's not a compact material anymore. It has a lot of damages. It has a lot of different phases which are forming, and you see the cladding, it's already in contact with the fuel. So then you can think that a lot of chemistry is happening there as well. So then if you know this chemistry, you can know, depending on what type of coolant you have, you can realize what kind of reactions you will have with the coolant before the coolant comes and escapes from the containment and goes out into atmosphere. So then you can predict and you can calculate the chemistries you can have, and also if something is going to be soluble in water afterwards, and if it's soluble in water, can go down into the soil and so forth. And of course, we have the fission gases, which of course from one pin is not much, but if you think about the core, then you have quite a bit, and you have a lot of iodine released. And of course, iodine is known that is one of the first which are going to affect a human being if it's released and if it's enough concentration of it in the air. So of course, this is a very important part to be known and to be studied. So as you can see, this is cut through a high burn-up of a fuel. This has been a metal alloy, so it's not an oxide alloy, by the way. So I think that we are going to the next page. In order to think how many things can exist and how they can be, if you look a little bit at the burn-up, so it starts very slowly to form different phases. So you look that you have a burn-up, which is in the beginning of the cycle, and then you can go to the next. I'm talking about the picture which is on the right-hand side down. You can see how the differentiation of the phases start to happen, and how you can see the migration of different phases going towards the outer rim and close to the cladding. So you can see very well that you get first you have the rare gases and the volatiles forming on the outside part, so they are migrating towards the outer part of the fuel, and then you have the metallic precipitates. You see that you have ruthenium, palladium, and so forth. So you have all these forming precipitates, which is the next part on the outer sphere. Then you have the oxide precipitates, which are getting quite close towards the middle part. And then you can have also a solution of the oxides, which can, depending on the temperature, of course, you can have different phases which can be formed. And towards the middle, you have the higher actinides, which are going to be there. So basically, they will go towards the center part of the fuel after higher burnup, so irradiation for a long time in the reactor. So you see that it's very easy to actually follow and see and to know where these phases are. And knowing this, you also can judge which one of them will come first out. and what phases, what chemistries they will form when they are coming out and meeting the coolant. So this, of course, is very important because this way you know also the time which it takes for these to come out, and also how they can be released further into the nature if there is an accident which is with an open reactor site. So it's not the containment, it's not integer anymore. Next, please. So basically what we were talking until now is this, that in the beginning of life, we have a beautiful stack of pellets. Everything is in order. Then you have the fuel a longer time in the reactor, and then depending on the type of the fuel, of course, not all the fuel is swelling that much, but let's say oxides fuel are swelling quite a lot. And then after one cycle, this is of course an extreme case you see here after one cycle, but after one cycle you can get a lot of swelling and a lot of deformation of the initial nuclear fuel. So these can provoke rupture, and then you can see how the previous phases can be released into the coolant. So we are going next, please. And when you have this type of swelling, you see, I'm not sure this is the best pictures you could see, but I take them myself, and I apologize for my skills, but you can see that the swelling can look like that. So what happened is basically that it's not only swelling, but it's disturbing the neighbors. That means that you will have all the condition to damage other cladding tubes around it, and that means that from your nice stack of tubes here, you actually can get quite a lot of damage. And here you see that due to the pressure, it already exploded. So the bubble probably here was either a defect, or you had a difference in temperature because something was stuck on it from the outside. And of course, then you have another temperature inside the tube. So you could see how things can happen, how the accident development can be from the swelling, then you get the release of the fuel. And if you look at the size of these holes here, you can imagine that basically almost a full pellet can be ejected from the cladding. Next, please. So when you think about ejection of the cladding and all this, and we talked that the volatiles are coming out, here we have an example, only iodine. And from the iodine, you can see how much chemistry can happen only because you have radiolysis. This is in the case of water. You have radiolysis, you have from control rods some interactions with silver or cadmium, and then you form different chemical compounds which can or not dissolve in the water. If they're not dissolving in the water, you see that you have the dissolution here, then you might have some precipitates. Like here, you can have precipitation, you can have absorption and desorption, so this can go back and forth. You have a lot of chemistry where it's, how should I say, you have a lot of reactions which are basically reactions which will eventually reach equilibrium, but you can see that there are a lot of reactions which until they reach equilibrium, they can form different phases, and they can generate all kind of phases which they shouldn't be in the water in a reactor. So all these phases which are formed here, if the reactor is damaged in a way that the vapors can come out, all this chemistry will come out with it. So here we are only talking about the iodine chemistry. Of course, there are other materials which are not so easily reactive, which are more inert than iodine is, but some of them are actually even more complicated chemistry. So if you think about this, all this chemistry could be predicted because we know what and how iodine can react at a certain temperature and certain conditions, and what materials are close to it, which can provide, for instance, other materials which can interact and react and form another phase. So thinking about this safety of a reactor, it's a lot of lesson learned from the past and a lot of developments in chemistry and in reaction chemistry, which we achieved to the level that today we can predict this kind of behavior. Next, please. Also, when we think about fuel coolant interaction, and I told you that this is very interesting, the chemistry has been studied quite a bit, and a lot of aspects are known. We have, of course, different type of chemistry compared to what type of coolant we have. And the current studies for the generation 4 reactors we are studying today is the fuel and LBE, as I said, so these metallic coolants. And we are studying this in Europe. We have in MOL a lot of work going on, where we also have the research reactor called MIRA. KIT and GRC in Germany, of course, they have a lot of setups and loops where they are studied this. We have ENEA in Italy and also the universities associated in Italy. And then we also have research going on other places like in Sweden and also other countries in Europe. So what can we say about that? Well, the metallic coolants, they do have some clear disadvantages. That any impurity which enters the flow of the melted material can be possible a seed, like seeding point for crystalline growth. So basically you are growing crystals on the surface, and if you do that, we know that that can block channels, and then if the channels are blocked, then the coolant flow is not working properly. That means that we have areas where the temperature is going to be very high, and then we have the swelling, and then we have the potential holes they will produce, as you have seen earlier. So if you look at that, even in the current fleet of reactors, we have problems with things which are growing on the surface of the tubes. And here I'm talking about the crude growth. So crude crud is basically all kind of aggregates which can exist from the water, impurities and so forth, and eventually they will come and react with the surface, which offer the best chemistry to get close to. And of course, this is a good chemistry. That means that you will get all kind of compounds, and then you get this kind of growth, which have to be cleaned. Otherwise, the reactor will have problems, both with the water flows and also some points where the temperature is not the same as in the areas where it's clean. And of course, all these stories, both in the light water reactors and also in the future generation 4 reactors, can lead to fuel failure during the operation. And this is something which we want to avoid. Next, please. So I was talking about the MIRA reactor. It's a reactor. It's a research reactor which is projected and on the way to be built in Belgium at the CKCN area in MOL. I'm sorry. And it is a multi-purpose research reactor. It's very beautiful. You can read a bit more about that later. But basically what we are looking at and what we have a lot of research going on is the lead bismuth coolant and the interaction with the fuel. If you can go further. Okay, so one of the projects we have been looking is called SEARCH, Safe Exploitation Related Chemistry for reactors which are cooled with metals. Next one, please. And some examples is what do we look at? Well, we can look at the lead bismuth, which has an eutectic point of 123 degrees, and it's quite good because the boiling point is very high. That means that you have a very good coolant for the reactor. And then you have the possibility to have different type of fuel which can be used there. And then we looked at the interactions between the fuel, the coolant, and the cladding. And the proposed material is the one I told you before, is the titanium 1515, so it's not a zircaloy anymore in this case. Next, please. And what basically we have looked at, what happens with the volatiles, which the ones which are coming first out from the reactor, from the fuel when something has happened. So we looked at iodine, cesium, ruthenium, and then we have the reference, which is basically the samples we need to compare with. And then we look at different temperature, what is happening and what we could collect from the surface. You see that the colors are varying quite a bit because we have had different materials forming. So if we now go to the next one, then we could collect the samples and we analyzed with XRD the results for iodine, and we found out that we have a lot of compounds forming depending on the temperature, which is also very good to know. So when you make a calculation for the safety reasons, you have to know what phases are forming at different temperature and also different compounds. Next, please. And the same with cesium. You can see that in the case of cesium, you have probably even more interesting chemistry than with the iodine. You have a bit more reaction. The temperatures are good for this type of reactions. Next, please. And ruthenium also is forming quite a bit of compounds, which at the point, some of them can be soluble in water, while others will be quite inert. And when you find out that something is inert, that means that also you know that not all these compounds will damage or will be dangerous when it comes out in the nature and probably not reacting with anything. That means they cannot be transported further so easily. Next, please. So to wrap up, basically everything we said so far about safety of a reactor is that chemistry and chemical approach are a very important part of the operation of a nuclear reactor. And we have had a lot of lessons which we learned along the years and also from the beginning, from the Oklo reactor, where we could see what compounds have moved and how long they have moved in nature. Then we also know by now that the right chemistry combination of the fuel, cladding, coolant, and the surrounding material are the base of the safe operation of the reactor. And why I say that is that you remember that I told you that when you have certain materials which can be a catalyst, then you might not want to have this happening, because then you can have other damages happening. The mechanism behind all the chemical processes happening during normal operation, including structural material, they have to be well known, and you know the mitigation measure you can take in good time. And then you also know that when you know all these details, the further processing of the resulting waste is easy and is dependent basically on the results of the both initial chemistry as well as the final chemistries you have when you get the fuel out from the reactor. So to conclude the lecture today, basically the chemistry of a nuclear reactor is what actually is safety of the nuclear reactor. So I would like to thank you very much for listening to me, and now if we have time, then I would take questions. Thank you. And I would like, of course, to acknowledge all the projects we have been working on, and also Chalmers University for making possible to study all this part of the reactor safety. So, thank you.
Thank you very much, Teodora, for your very detailed and interesting presentation. I think that it will be an occasion for stimulating our students, our young scientists, in approaching this kind of research field, because there is a lot of interdisciplinarity between engineers, chemists, physicists, and so on. And it is a very, very challenging field of research. I have a curiosity.
Sure.
Since you are from Romania, and in Romania is a lot of effort is dedicated to Alfred. Do you know if how is the situation, if the demonstrator is in a good evolution?
Well, what I can say about Alfred, I'm currently working in Sweden, but what I can say about Alfred is that we have a very serious consortium, which is called Falcon, and that is basically the consortium dedicated for Falcon Alfred demonstration. We do have a lot of work going on. We have a project, European project right now, which is called Pascal, where we are looking at the safety of Alfred. So basically, there is a lot of work going on for the cladding coolant interaction. The coolant is going to be lead. The cladding right now is going to be most probably an austenitic steel. And also, when it comes to the fuels, we are looking currently at nitrites, but we are also considering other potential fuels. So what I can say is that right now we have a lot of data, and we are working for the safety of the reactor when it comes to the primary parts of the fuel and the coolant, and also the surrounding material interactions. So we are exactly in the beginning of closer to the core. And Alfred is actually a long time commitment from the Romanian government with the help of European Union, and also we have a lot of collaboration with Italy because it's one of the main partners in exactly. So Alfred is well on the way, and I would say that together with Mira would be the two sites in Europe where we have the real demonstrators for lead-cooled and lead bismuth-cooled reactors.
Thank you.
Thank you.